So let's have a look at this problem now where we've got the box and two forces acting on the box. So here's the question and the box with the two forces given in the question. And I'm going to just add all of the other forces that we need to complete the force diagram. We've got the reaction from the surface on the box. We've got the weight of the box. And we've got friction opposing the intended motion. So the first thing I can do is to resolve in the direction shown. And when I do that, I get the component of the 65 Newton force is 65 cos 28. The component of the 35 Newton force is 35 cos 15. And then we've got friction in the opposite direction. And that all equals mass times acceleration. Acceleration 0 because it's in limiting equilibrium. So from that, I can calculate that friction is 91.2 newtons. Now, when I resolve vertically, I get 65 sine 28, which is the component of that force in that direction. R we've got in the same direction. Then we've got minus 35 sine 15 in this direction, and then the 150 newtons there. And so that's the resultant force vertically. Again, that equals 0 because the acceleration in that direction is 0. From that, I get an R of 128.5 newtons. Now, because the box is in limiting equilibrium, I can use the fact that the friction is mu times R. So therefore, mu is the friction divided by R, friction divided by R, which is 0.709. So that's the coefficient of friction between the box and the surface. Now what we're looking at is the 35 Newton force is being increased to 85 newtons. So this force here is being increased to 85 newtons as shown. So now we're going to do a very similar process again, resolving horizontally first. The difference this time is that the resultant force, we changed the 35 to 85, but the acceleration is no longer equal to 0. It's equal to the mass times the acceleration. Well, the mass is the weight divided by 9.8, because this force would normally be mg. So if we've got mg equals 150, then m is 150 over g. So now I resolve vertically, and that's very similar to last time. Except the 35 has been changed to 85. And from that I can find the normal reaction is increased now because the downward force has increased. So we know that the box is moving now, it's accelerating, and so once again friction is equal to mu times R. So mu we know is 0.709. The normal reaction that we've just calculated here is 141.5. So the friction just over 100 newtons. So now we can put that back into this equation here and calculate A to be 2.56 meters per second. So there we are.